So let's get started. Today I want to talk about introduce the non-crossing and the one-crossing approximation for the quantum impurity models. Because this talk will be recorded for later usage, so I will begin the introduction from the very beginning. And
Lei, do you want us to ask questions right away, or you want us to ask questions at the end?
right away.
Right away.
Yeah. And so if you have any question, just ask me. This is an overview of this talk. First of all, I will introduce the notations, the setup of the impurity models and the hybridization expressions. Second, I will introduce how to derive the self-consistent equations for the hybridization expression. And third thing, I will introduce how to do the measurement. Finally, I will introduce my NCA OCA solver, how to run that, and what every parameter means. So let's get started. So for the quantum impurity model, it usually has three parts. Each local, each base, and each half. For each local, it means the Hamiltonian for the impurity. It usually has two parts. One part is the non-interacting Hawking term, and the other is the interacting term. And by the way, we should be careful about this notation. Usually we use IGLK, not IGKL, in our simulation. And each base is the Hamiltonian for the base, which is quadratic. And each half is the coupling between the impurity and the base. And the parting function is a trace over this e to the minus times the total Hamiltonian. And we can separate the total Hamiltonian into two parts, HA and HB, and express the parting function in this time ordering representation.
Right. You said that already. Your notation for the H1 local is very much non-standard. Right?
Yeah.
UIJKL, DI dagger, DJ dagger. That's very different from how it.
That's standard. It is right that you have to have KL here, but LK in the other.
That's right, but okay. Fine, go on.
This is in 1122 notation, right?
Yeah.
I think that's supposed to be used in the other.
But this is how all our Hamiltonians are listed. So it's precisely true that one has to be careful not to say IJKL and then IJKL one more time.
That's right, but our UIJKL would be UI. Well, anyway, okay. Let's move on. Yeah, one has to be careful, and you just have to define it.
Yeah. And next, I want to introduce what the hybridization expression. So in hybridization expression, we treat HA, the background, as H local plus H base, and HB equal to H hat. So in the background, there's no coupling between H local and H base. And we do the type expression regarding to HB like this. And it can be simplified by some complicated calculations. And I have a note for the detailed derivation. If you want to look through the derivation, I will. This note will be uploaded on our homepage later. So here I will just briefly introduce how to do that. So this expression can be simplified according to the following observation. First one is for the coupling Hamiltonian. It has two parts. This H tilde have and H tilde have dagger. And for each term, it only contains one base operator, C or C dagger. And because we finally need to do the trace, the total number of the base electrons had to be conserved. So that means only even K, the only even term with equal numbers of H tilde have and H tilde have dagger can make a non-zero contribution. And also because we treat HA, the background, as H local plus H base, there's no coupling between the base and the impurity in the background. So they can be decoupled from each other. So the trace over the whole thing equals the trace over D times the trace over C. They can be decoupled from each other. And finally, we notice that in the background, the H-base is corrected for the base electron. So we can use Wick theorem to simplify the expression. So far, any questions? And this is the definition of the hybridization function in the imaginary time. If you can do a Fourier transform to get delta I omega, and you will find they are consistent. And after the definition of this function, so this is the final form of the hybridization expression. It's a little complicated.
So Lei, when the epsilon vanished, because you have like this VR, the
Here?
yeah,
You mean the epsilon k?
yeah, like on imaginary frequency it would be like V, right? Like delta ij would be V I k times V k j, right? Divided by omega minus epsilon k.
Yeah.
So
Here.
the epsilon k.
Because we are doing the average, the epsilon k comes from this one.
All right.
So non-interacting Green's function can be written as, 1 over frequency minus pole location.
Right.
That's exactly that Green's function.
Okay.
Yeah, this part contains the epsilon k. And okay, so this is the final expression of the partition function in the hybridization expression representation. So the configuration space is a little complicated. It's mainly described by 3 parameters. K is the order of our expression in the Taylor expression. Tau means tau is the vector tau. It means the time for the D and D daggers here. D and D daggers. And by the way, the D's and D daggers are time ordered separately, but there's no specified the time ordering relation between D and D daggers. And the J is the corresponding flavor for each operators. And this is an exact result as long as this perturbation is not infinitely large. So if we perform the CT-QMC, we will get a numerical result, numerical exact result. So we can do 2 steps. There are mainly 2 methods to perform the simulations. First method is CT-QMC. So we sample each configuration according to its weight, W local times the determinant of delta. This method is numerically exact, but it may suffer from severe sum problem, leading to the exponentially growing errors. And the second method is called self-consistent resummations of diagram in the literature. That's what it is called in the literature. And the NCA and OCA are 2 frequently used methods. The benefits of the second method is it will not sum from sum problem, because we only need to iterate 2 self-consistent equations later. And another benefit is the computational cost only scales polynomially in the system size.
Is that correct, Lei?
Which
Is that
one?
correct?
Which one?
The computational cost scales polynomially in system size?
I think so.
Well, the Hilbert space grows exponentially, right? And with that,
yeah. But this sentence, I read this sentence from a literature.
well, that doesn't mean it's correct, right? And that's a bad justification. But I think what was meant here is that it grows polynomially, as a function of temperature, for example.
Yeah.
But as you add new orbitals, this becomes exponentially more expensive,
Yeah.
as you've seen yourself, right?
Yeah. It was this real scale, 2 to the 2 times the nth power.
Yeah. So I would be very careful with this. That it's at least a little bit more
Yeah.
explained.
But it's still more efficient if it has some central. And finally, the disadvantage of this method is it's not numerically exact, and it's also not easy to estimate the systematic errors. Okay, this is the warm-up, and let's go to more details. Let's go to more details of this self-consistent resummation method. First of all, to derive, the main goal is we want to find the self-consistent equations for the hybridization expression representation. And to do that, we first need to expand the configuration space by a little bit. So you may remember that in the expression of the hybridization function, we have this term. The determinant of the hybridization functions, it has k factorial terms. And we expand that, we can solve that as k factorial terms as all possible pairing between tau and tau primes. And then for each pairing, we just represent the curves connecting to the corresponding pairs. And these curves called the hybridization lines. What that means is we expand the configuration space by introducing one more degree of freedom. That degree of freedom is the pairing between tau and tau primes. And you can write down its contribution as follows. And after we expand our configuration space, we can define the pseudo-particle propagators. The bare propagator equal to the e to the minus h log tau. And the rest propagator is, actually this expression is very similar to the hybridization expression of the partition function. The only difference is we remove the trace. So if you take the trace, you can recover to the partition function immediately. And this is a typical configuration of the R tau. So this is the third order, configuration. We have 3 times tau 1, tau 2, tau 3 for the D's, and tau 1 prime, tau 2 prime, and tau 3 prime for the D daggers. And tau 1, tau 2, tau 3 are time ordered. Tau 1 prime, tau 2 prime, and tau 3 prime are also time ordered. But the time ordering between tau and tau prime are not specified. And we also need to pair different D and D daggers. Here in this example, the first D is paired with the final D daggers. And also, you can see that. And also for the hybridization line, you can understand that as follows. So at time tau 1, there's one impurity electron hopping into the base. And finally, at tau 3 prime, this electron hopping into the impurity again. And if for the left arrow, you can consider that as at this time point, the base electron hopping into the impurity, and until tau 3, it hop back into the base again. Any question? Okay. After we understand the configuration of our tau, we can construct any configuration as follows. Step 1, we just choose an order k. Step 2, we specify the values of vector tau, which fulfilling the constraint that the tau and tau primes are time ordered separately. And finally, we pair tau and tau primes using the hybridization lines. And for each configuration, you can write down its contribution by the following. It equals an overall sign, which will be analyzed later, times the contribution calculated from this small segment. And we should be careful that in this in our diagrams, the right direction corresponds to the time increasing. However, in the expression here, because the conventional t tau, the left hand side corresponds to the time increasing. So you should be very careful about that. And the overall sign comes from 2 places. Place 1 is the time ordering between D and D dagger operators. And the second part is the pairing between tau and tau primes. And I will show you later a very straightforward way to determine this overall sign. Next, we want to find the self-consistent equations for the rest propagators. Equation 1 is straightforward. It's Dyson equation. That means S is the self-energy of the corresponding pseudo-particle propagators. and S is a set of all one-particle irreducible diagrams. And our question is, we want to find another equation to connect S and R again, so that we can iterate to get a convergent result. And we notice that the structure of S tau is very complicated because it has many crossover points. And so we need to do some approximations to get a simpler expression.
So I should probably say here that, you call this a Dyson equation, and that's probably, certainly with this figure here, it's clear that it is of the structure of a Dyson equation. But it's very different from the Dyson equation in like the usual in imaginary time formalism, right?
So I call here pseudo particle.
Exactly, it's really a Dyson equation for the pseudo particle propagator. So it's a very weird object if you're coming from standard kinematics. So just as a word of warning, but it has exactly the same structure.
Yeah, maybe I just So we need to do some approximations to get another equation connecting S and R. So here comes the non-crossing approximations. For this approximations, we only consider configuration without any crossover points. So that means the D at the very beginning must have to be paired with the D dagger at the very last. Otherwise, it's non-irreducible, or it must have some crossover points on D dagger D. That's the first order. And also the sign will be analyzed later. The second approximation is a one-crossing approximation. So it's a higher order. It's a higher order improvement for the NCA. In this approximation, we consider the configuration which has at most one crossover points with all other lines. And we can analyze a self-similar structure and write down this complicated expression. Finally, I will introduce how to determine this overall sign. So in the literature, people usually use the Latinger word functional to analyze that. But I found a more straightforward way to do that, to analyze the overall sign. The main idea is to find the connection to the following configuration, which we know has a plus sign. So this configuration is tau 1 prime less than tau 1 less than tau 2 prime less than tau 2, etc. And the ice D is paired with the ice D dagger. From the first thing, we know that the sign coming from the time ordinary of D and D daggers is +1. From the second one, we know that the sign from the determinant is also +1. So we just want to find the connection to this configuration. And to do that, I found we need to do two elementary movements. One is we need to move a hyperdeterminate line across a complete graph. And another is we need to switch the order of this hyperdeterminate line. And I found that the first step will not change the sign, and the second one will change the sign. You can find more detail in my note if you are interested. And just examples. Let me use this that two elementary movement. We can find the expression of S0 tau and S1 tau. The plus one that is one here.
Another good way of you unplugged there. Another good way of finding these things. Yeah, is the trace has to be cyclic. So if you take one of those vertices and you move all of the vertices by the same amount so that one wraps around to the beginning, then the sign has to stay the same. And that's a good way of debugging your signs and also checking that you're having the right.
Yeah, in the next line I will introduce more apparent. So once we use that to as a military movement, I can prove this following statement. The conclusion one is if we want to get the expression of S tau, we just need to replace R by R0 in the second energy expression. Evaluate this, the overall sign in this case, and then replace R0 by R again. Then we will get the correct result. And the second one is to get that overall sign, we just need to count how many right arrows and crossover points to get the overall sign. So why we use right arrows, not left arrows? That's because here in the expression of the hybridization function, we use C dagger. If we use C dagger C, then we will need to count the left arrows instead. And because these two simple conclusions, we can even do improvement over NCA OCA. First of all, we need to choose an order n. If n equals 0, then we will get NCA. If n equals to 1, we will get OCA. And n equals to 2, we will get a subset of the two crossing approximation. So we can write a MATLAB or Python script to get the analytic expression for that. But currently, because OCA is already very slow, so maybe not, it doesn't have much usage. So far, any questions?
Maybe also comment that the inch-worm method is, something very similar, where, at zero crossing or cutoff at order 0 or order 1, you get NCA, cutoff at order 2, you get OCA, and then you can gradually converge inchworm, and we have cases where inchworm has to go to very high orders. But we also have cases where the system is not really hybridizing that much, where inchworm actually converges very fast. So Andre is an expert for any sort of question on that.
Yeah, also, we are doing the parallel programming.
Of course.
Okay. Okay, let's continue. I think I want to introduce how to do the measurement. So here we already get the self-consistent equations 1 and 2. Then what we need to do is iterate these equations and get a convergent result of the pseudo-particle property. And after we get that, we can do the measurement. For the static quantity, because we know the once we take the trace over R, we will get the particle function. So we can get the static quantity easily by doing the trace. And we can also evaluate the dynamical quantity. For example, the single particle Green function using these two expressions. This one is for the NCA, and this one is an improvement for the OCA. And I should say that. So that's what I use in my code, but there's a disadvantage. The disadvantage is for these two equations, that they don't take the vortex correction into account. So the solution is just consider the vortex correction. However, the idea, the theoretical idea is very simple. So we just need to calculate the vortex correction. However, to do the program, to make the code, is almost unaffordable for multi-orbital cases, because we need to enumerate all the input and output states, and it grows exponentially. So currently I just use these two expressions for calculating the single particle Green function. Okay, finally my code for the NCA OCA solver. So I call it XCA solver because X can be a variable. It will be unknowable. It's on the GitHub here, and the dependence of my code it depends on two libraries. Library 1 is the abscol, and library 2 is the eigen library to use the matrix operation feature. And to run my code, you only need to do 3 steps. Step 1, you need to prepare the input file, which I will introduce later. And then you need to change the input parameters accordingly. Finally, you just run this shell script, which means you use CMake and make build the project and then run this code. And for the input, so that's why I want to introduce the notation here. So for the input file, currently it supports two kinds of input. One is completely compatible with the ED, so the ED input. This is the correspondence between this theoretical expression and the corresponding data notation. Here, be careful that this is the convention in ED input is ij sigma, not sigma ij. And it's also compatible with this is the data given by China. I think it comes from the GW simulations. And this is also the correspondence. So here we use sigma ij, not ij sigma. And interaction is only dependent on the orbital index, regardless of sigma prime. And because different server has different formats, so my plan is to write a Python script to get a uniform input format to run my code. And the output of my server are the top mesh and the single particle grid function, which has this convention. Ij are the orbital index. Sigma I, sigma g are the corresponding spin index. And this is all my input parameters in my code. This column is the real value I used in the simulation of the EG orbital of the manganese oxide. The first one is the number of orbitals. The second one is the number of spins. Currently, my code only supports spin one-half system, but if needed, I can generalize that later. The third one is the beta. This one is the system temperature. Max iteration is the maximum iterations I use in the NCA or OCA iterations. And precision is just the precision of this solver. So once we reach this precision, the iteration will stop. And this one is the number of slices. Currently, I use uniform mesh, but maybe I will use non-uniform mesh later. This one, you should be careful that this n slices is the number of slices. It equals the number of time points minus 1. So, by the way, for the number of top points, 0 and beta are included. And this operator to determine whether we need to do the cutoff or not to detect the symmetry. This one is whether we choose to perform the SC symmetry. If we set it's true, it will detect the SC symmetry. If the SC symmetry is not conserved, then the code will stop and warning used to set this to false. And this just whether we choose to run NCA or OCA. This parameter is discretized, means whether we need to discretize the base. If it is equal to false, then the input should be the delta function directly. If it is equal to true, the input is epsilon k and vk. And finally, the input and the output file here. Any question about that?
So I should probably clarify that there's never any need to discretize a hybridization function in NCA or OCA. But if you want to check against what, for example, exact diagonalization gives for a certain discretized version of hybridization, you can, artificially introduce the fitting errors into the NCA and then compare to what the ED gives for the same problem. The whole thing is a trade-off, right? NCA is an approximate method, but it doesn't suffer from any bad fitting or bad discretization error. And ED, of course, is an exact method for a discretized hybridization, but it suffers from the discretization error or a fitting error of your hybridization. And at the moment, we don't know which one of those problems is more serious. So that's one of the reasons why we're looking at this now with these NCA OCA solvers.
Yeah, maybe I will write a Python script if we fit the best, maybe I will do that before input to the signal class. And here's the notation I use. So the first entry of the state is the upspin state in the zeroth orbital, and downspin state in the zeroth orbital, and then the upspin state in the first orbital, etc. This is the notation I use in my code. And I labeled these different bases as follows. So I just take this as a binary expression and calculate its decimal expression of the value. And then that's the corresponding label. So 0, 0, 0, 0 is 0. 0, 0, 0, 1 is 1, like this. That. And maybe I don't need here I just did a little modification to accelerate the calculation of the block diagonalization. So here is I will introduce how to do the block diagonalization later. So the main thing is to find the transformation matrix to change the order of the bases. And I noticed that this matrix is a sparse matrix, and all the entries all the non-zero element is equal to 1. So it can be simplified it can be accelerated to calculate this transformation in the new basis.
So Lee, you keep all the up and down strings together, right? You don't separate them. You keep all the up and down strings, right? For all the up and down electrons together. You don't separate them, right?
So you allow for off-diagonal hybridizations, I think that's the question.
No. No. So for example, in a non-relativistic approach, you could separate all the up and down spins, and then write the resulting matrix is a direct product of them.
Oh.
So in the non-relativistic thing, one can do it like that. But for example, if you wanted to work with relativistic Hamiltonian, then keeping them together is necessary. So.
Yeah. You mean the upspin? If we group this data as upspin and downspin, it will be block diagonal.
Yeah. So it would be block diagonal, and your dimension of Hilbert space would drop, right? Because you would not need to have that product. But if you want the relativistic case, then you cannot separate them.
Yeah.
So
I think I didn't separate them.
So that's okay. One can do the relativistic Hamiltonian directly that way. But I think if we wanted to study non-relativistic case, it may pay to separate them, because then your dimension of the Hilbert space will drop a lot.
So yes, and there are other things that one could also do here. There's a bunch of optimization that we can go through. I think that's a second step, because first we have to establish how useful this technology is, because we don't know how bad the NCA OCA approximation is going to be in practice.
But people did.
Well, the fact that people did some of these calculations before doesn't mean that it's a good approximation. Also, people never did off-diagonal hybridizations with any of this. So that's...
What do we know about OCA and NCA for like 2D Hubbard? Like how well did it work?
If you're in the insulating regime, it's fantastic. If you're not in the insulating regime...
Insulating means like mod, or means like...
Doesn't matter, right? Anything away from the Fermi surface, this thing doesn't hybridize, and it's great. Anything that is dependent on subtle behavior at the Fermi energy, like Kondo peaks and things like that, the height of the Kondo peaks are off, the width of the Kondo peaks are off, it's not a technology that gives you like very subtle correlation physics at the Fermi energy. But it might just be good enough for many of the applications we have. The non-interacting limit in these things is very difficult. So non-interacting in the sense of, U equals 0. Right? Because U equals 0, you hybridize the most, particles fly all over the place, and the approximation gets bad. But the moment you have some sort of blocking in your system or some sort of band insulator, this works very well. So if you think of the F electron systems, for example, where you just have F electrons lurking around, but you're not actually participating in you know, any physics, this should be fantastic.
I think this is really the magnitude of the hybridization that matters, and I don't know, like if you transform Hubbard to different bases, just should be much better. Is that true? That if you did the Hubbard in the, you know, in the bases that like not in right on-site orbitals, but the linear combinations which diagonalize the hybridization into these 2x2 blocks, that already should become better.
I don't know. Not clear to me.
Currently, I just use the orbital matrices. This is how to do the block diagonalization. So the symmetry usually depend on the exact form of each local. But usually, we know that the total pattern number and total SZ spin are conserved. So what we need to do is switch the order of the bases so that states with the same N and SZ are grouped together. And after do that, the each local is block diagonalized both, and it should be faster than before. And the data structure I used in the block diagonalization is here. I use math vector. So for example, for this matrix, I use a vector which has 16 elements. The elements 0, 5, 10, and 15 are this matrix. And the other elements are 0 by 0 matrix. Why I also slot the blocks here? Because also for the H local and the R0 is block diagonalized. But for the D and D dagger, it's sparse, but the non-zero element is not in this block. It's in here or here. And for the dress propagator R and the self-energy, it may or may not can be block diagonalized depending on the system you simulated. So this is the uniform format I use in my code. And I also use some operator overloading so that this whole vector can be can we do the addition, multiplication, scalar multiplication, and constant shift directly. So if you want to use the block diagonalization in other solvers, maybe you can just you use my code in this part. So because I have an exam right after the talk, so not right after, several hours later. So I think I will stop here and open to any questions.
All right, thanks.